The 8255 is like a small kitchen helper for a microprocessor. The processor is the chef who can only prepare a dish when the ingredients are ready. The 8255 PPI Programmable Peripheral Interface hands the chef fresh vegetables, fruit, or spices by turning parallel data lines into easy-to-use ports. You pick the 8255 when the processor needs to talk to several external devices, LEDs, switches, AD converters, printers, at the same time, and when you want a cheap, simple chip that can be programmed for input, output, or handshaking. The selection criteria are: 1. The processor's bus width matches the 8-bit data bus. 2. The address space can accommodate 3 port addresses plus 1 control register address. 3. You need flexible port direction, input or output, and optional handshaking. 4. You want interrupt capability without adding another chip. If these match, the 8255 becomes a perfect sidekick. 8255 comes in a 40-pin DIP. Think of the pins as the legs of a table. Some hold the table steady VCC and GND, some are doors to the kitchen, a 0 to a 7 address lines, D0 to D7 data lines, and some are switches CS bar, RD, WR reset. Power is 5 volts plus or minus 0.5 volts, and the ground pins must be tied together. For physical interfacing, you need to tell the processor when you want to talk to the 8255, look at address X. This is done with address bus decoding. For an 8085, you might use address lines a 0 to a 1 to select the 4 internal registers port A, port B, port C control. A simple decoder uses 274LS1383 to 8-line decoders. The enable pin of the 8255 CS bar is the output of the decoder, and the lower address bits are fed directly to the 8255's A0 and A1 pins. Mathematically, CS bar equals not open parenthesis a 15 and a 14 and ... and a 2, and not a 1 and not a 0 close parenthesis if you map the device to the highest address of a 64 kilobyte space. The reset pin must be pulled low for at least 100 nanoseconds to clear the mode register, then release to high. The mode register is the 8255's instruction booklet. You write an 8-bit value to the control address to tell the chip how each port should behave. The programming steps are: pull reset low for greater than 100 nanoseconds, then high. This clears old settings. Output the control word on the data bus. Assert CS bar low, WR bar low, and keep RD high. This is a write cycle. Release WR bar high, then CS bar high. The control word has bits. D7 equals 1 for mode set, D6-D5 equals group a mode, 00 equals mode 0, 01 equals mode 1, 10 equals mode 2, D4 equals port a direction, 0 equals output, 1 equals input, D3-D2 equals group B mode, only mode 0 or 1, D1 equals port B direction, D0 equals port C upper/lower direction. Example for mode 1 on port A as input and port B as output. 10001010 base 2 equals A to hex. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. When the processor wants to read or write the 8255, it follows the same dance as crossing a street with traffic lights. The control signals are: CS/chip select green light to let the 8255 listen. WR/write low means the processor is giving data, high means idle. RD/read low means the processor wants data from the 8255. The timing diagrams. Number 1, address bus is stable, CS/goes low. Number 2, for a write, WR/goes low while data bus holds the byte. After T sub PW approximately 150 nanoseconds, WR/ returns high. Number 3, for a read, RD/ goes low. After T sub AC approximately 150 nanoseconds, the 8255 puts data on the bus. RD/ returns high after T sub PH, approximately 150 nanoseconds. All these must happen while the processor's clock phi is in the appropriate state, usually the second half of the T state. The bus cycle integration simply inserts the 8255's address and control signals into the normal machine cycle of the microprocessor, just as a bus stop is added to a regular train schedule. Port C is the 8255's handshake helper, like a classroom hand-raise system. The 4 bits of port C can be split into 2 groups: upper C7 to C4 for group A handshaking, and lower C3 to C0 for group B. The main signals are: STB strobe tells the peripheral that data is ready. ACK acknowledge the peripheral pulls this line low to say got it. IBF/OBF input/output buffer full internal flags set by the 8255. When using mode 1, the sequence is CPU writes data to port A, then pulls STB low, port C bit becomes 0. The external device, after reading the data, pulls ACK low, which the 8255 senses, and then clears the IBF flag, allowing the next byte. This two-way handshake ensures no data is lost, just like a child raising a hand STB, and the teacher nodding ACK before the next child speaks. The 8255 can ask the processor for help by raising its INT pin. Think of it as a buzzer when someone needs attention. In mode 1, when the OBF output buffer full flag for port B goes from 0 to 1, the INT line is asserted active low. The microprocessor must have an interrupt vector set up. For example, on an 8085, the INT instruction jumps to address 0x0038. The service routine typically saves registers, reads the status register port C to find out which port caused the interrupt, reads the data from the appropriate port A or B, clears the flag by reading the port or writing to the control word, restores registers and executes RET. The vector assignment is fixed by the CPU, for example 0x0038 for RST5 on 8085. ISR must be shorter than the time the peripheral can wait for the next data, otherwise data will be overwritten. Hash-defined PPI underscore B a SE0x20 / base address of 8255. Hash-defined PPI underscore CTR open parenthesis PPI underscore B a SE plus 3 close parenthesis. Void PPI underscore INIT open parenthesis void close parenthesis open brace. Outport B open parenthesis PPI underscore CT R comma 0 x80 close parenthesis semicolon / reset mode set. Outport B open parenthesis PPI underscore CT R comma 0 x8 a close parenthesis semicolon / mode 1 port A input port B output port C split. Close brace. Void right underscore port B open parenthesis UN8 underscore T val close parenthesis open brace. Outport B open parenthesis PPI underscore B a SE plus 1 comma val close parenthesis semicolon / port B address equals base plus 1. Close brace. Unsigned int 8 underscore T red underscore porta open parenthesis void close parenthesis open brace. Return in port B open parenthesis PPI underscore B a SE close parenthesis semicolon / porta address equals base plus 0. Close brace. If the CPU uses an auto-incrementing address for block, transfers the address for successive bytes is calculated as a sub n equals a sub 0 plus n times step, where step is 1 for sequential ports, for example reading port A then port C, or the size of the address space for a next device. The algorithm must also consider the 8-bit wrap around of the address bus if the base address lies near 0xFF. The data transfer routine often pull the IBF/OBF flags in port C before reading or writing to avoid collisions. While not open parenthesis in port B open parenthesis PPI underscore B a SE plus 2 close parenthesis and 0x01 close parenthesis semicolon / wait for OBF equals 1 before sending next byte. When wiring the 8255 to real hardware, think of it like connecting a water pipe to a faucet. You need a buffer so the faucet doesn't get damaged by a sudden pressure change. Buffer ICs such as 74LS244 protect the 8255 pins from high current loads and provide voltage level conversion if the external device works at 3.3 volts, while the 8255 runs at 5 volts. Pull-up resistors approximately 10 kilo ohms on input lines keep the lines at a known high level when nothing is driving them, similar to a door that stays closed unless someone pushes it open. Pull-down resistors do the opposite for active low signals like RD and WR. For level shifting, a simple resistor divider R1 equals 2 kilo ohms, R2 equals 3 kilo ohms can drop 5 volts to 3.3 volts, but a dedicated level shifter IC gives cleaner edges. PCB layout tips: keep the 8255 close to the microprocessor to short address and data traces. Use a solid ground plane beneath the chip. Place decoupling capacitors 0.1 microfarads within 5 mm of VCC pins, separate analog and digital sections, to avoid noise and root hand shaking lines with controlled impedance if they run long distances. These practices make the whole system reliable, just like building a sturdy bridge, instead of a shaky rope crossing.